So let's try another synthesis problem. Here we have 3-methyl-1-butene, and we're asked to synthesize this compound, Z27-dimethyl-oct-3-ene. The biggest clue here is the Z isomer. Alright, let's try it out. But we'll start with the same steps we did in part 1. Let's count the carbons on the reactant and final product and take some notes on the side and see what kind of synthetic sequence this could be. So here I have 5 carbons, and I'm guessing I have 10 here, but let's count. We have 3 here, that's 6, 7, 8, 9, 10 carbons. So like in part 1, we need to modify this compound here in 2 different ways, such that there's an electrophile to nucleophile reaction that adds 2 5-carbon compounds to form 10. Now the question is how to do that. Again, the primary nucleophile in this unit are alkynes, the alkynyl anion. We can make an alkynyl anion from this and attack an electrophile with 5 carbons as well. Add them together and we could end up with something like this. So let's take some notes. So again, very probable it's an alkynyl anion. But the question is, what kind of electrophile are we using? Because we don't have any oxygens here, it's just a hydrocarbon. So the chances are it's a primary alkyl halide that's reacting with the anion to form the 10-carbon compound. And again, we don't see any triple bonds here, we do see a pi bond, and again, the biggest hint was it's the Z isomer. So we need to end up with the Z isomer with the highest priority groups cis to one another. The only way to reduce an alkyne to a cis alkene is with these reagents, using powdered barium sulfate, coated with palladium, and poisoned with quinoline, which looks like this. That's what's called Lindlar's catalyst. So these are my initial reactions when I see this synthesis. A 5-carbon alkene, resulting in a 10-carbon alkene, probably through an alkynyl anion, primary alkyl halide, both of which are 5 carbons. React them both, you get a 10-carbon alkyne that's partially reduced with Lindlar's catalyst. That's to form the Z alkene. So this synthesis has many steps, but the goal is to form the nucleophile and the electrophile, react them both, and then reduce it partially. So let's start with the synthesis of the alkynyl anion. So I draw out 3-methylbutene, and I halogenate with Br2 in dichloromethane. That's to form this compound here, which is the substrate for double elimination. And to carry out the double elimination, we can introduce 3 moles of sodium amide base dissolved in liquid ammonia, and we should form the 5-carbon alkynyl anion. Again, note that the bond angle here is 180 degrees, so we have to draw it like this. Now we've generated our nucleophile, but what's the electrophile? We were guessing that it's the primary alkyl halide, which reacts with the anion to form the 10-carbon compound. So if we have an alkene to begin with, to form a primary halide, we need to react it with HBr, a strong acid, with bromine as the nucleophile, dissolved in peroxide. So I have my nucleophile, I've formed my electrophile. Let's mix them together in an aprotic solvent. So I'll call the nucleophile compound 1 and the electrophile compound 2. And the aprotic solvent here can be an ether, but let's use something different like DMSO. And this should be the product of that reaction. It should be 10 carbons, so let's count it up. We have 3 here, we have 3 here, that's 6, 7, 8, 9, 10. And once we have that, we can reduce it with Lindlar's catalyst to form the Z alkene. So we take our alkyne, compound 3, and in the presence of H2 and Lindlar's catalyst, we should get the Z alkene. So I reduce from a triple to a double bond. On the left side, I have an isopropyl group, which looks like this. And on the right side, it looks like isopentyl, I'm not sure. But we can just draw this out right here.